The rate laws we've seen earlier demonstrate the relationship between rate and concentration. However, sometimes we need to relate rate to time. If we use calculus and we integrate with respect to time, we can obtain the integrated rate law that shows the relationship between the concentration of A and the time of the reaction. Since calculus is not a prerequisite for this course, I won't do the derivation here. However, you can reference the text if you're interested in that derivation. Next, we will look at the integrated rate laws for the first, second, and zero order rate equations. For a first order reaction, we have the rate law where the rate is equal to k times a raised to the first power, as we mentioned earlier. If we integrate that rate law with respect to time, we get ln of a is equal to negative kt plus ln of a initial, where a initial is equal to the initial concentration of A. If we graph ln of A versus time, we get a straight line with a slope equal to negative k and a y-intercept equal to ln of A initial, and we can use this to determine our rate constant. So if we do this, if the rate is equal to molar per second, our k will have units of inverse seconds. Here we see a generic plot of the first order integrated rate law where we see ln of A at time t plotted with respect to time. We see that the y-intercept is equal to ln of the initial concentration of A, and we see that as time increases, the ln of A decreases, and we have a slope equal to negative k. So this will help us plotting time versus ln of A will help us determine our k. Conceptual Connection 15.3 asks, the reaction A forming B has been experimentally determined to be second order. The initial rate of 0.0100 molar per second at an initial concentration of A is 0.100 molar. What is the initial rate at A equals 0.5 molar? Well, here we're not relating time to concentration. What we're relating is rate to concentration. So we don't need to use the integrated rate law here. We're not having a time dependence. What we need to use is the regular rate law, and we see that it is second order. So the generic rate law for that is R equals K times A, the concentration of A squared. Alright, so if we plug in our initial set of conditions, 0.0100 molar per second is equal to K times 0.100 molar squared, we can solve for K and get our K for this reaction. And we see that K is equal to 1, and then our units are 1 over molar second. So if we then take that K and plug it into our new condition where A is equal to 0.500 molar, we see that the rate is equal to 1 times 0.5 squared. So our rate at the new concentration is 0.250 molar per second. If there are multiple reactants, then we have to get a little bit more complicated than our previously observed rate equations, where we had rate is equal to k times a to the 0, k times a to the first, k times a squared. We have to consider each reactant independently. So what we do is we change each reactant independently and see how that affects the overall rate for the reaction, and then we can determine the exponents of each of the reactants. So what we do is we take the data where we would say double A and observe the rate, double B and observe the rate, and we would get the exponent from that. And we're also going to see an equation that we can use to determine those exponents as well, if it's difficult to determine that by simply looking at the data. and making a qualitative observation. So we say that, let's say that our m is 1 and our n is 2, then our rate equation would be first order with respect to A, second order with respect to B, and third order overall. If our A was 2 and our B was 0, let's say, then we would have 0 order with respect to B, second order with respect to A, and second order overall, and we could simplify our rate equation to be equal to some k times the concentration of A squared, right? Because anything to the 0 power is simply 1. So let's consider conceptual connection 15.4. This reaction was experimentally determined to be first order with respect to O2 and second order with respect to NO. So I've written the rate equation here. The diagrams shown here represent reaction mixtures in which the number of each type of molecule represents its relative initial concentration. Which mixture has the fastest initial rate? So we see here that the rate equation is more dependent on the concentration of NO, and the NO is given as the red and blue sphere. So the conditions that have more an NO initially would be C, and that's going to be the mixture with the fastest initial rate. Next, we'll consider the integrated rate law for a second order rate equation. If we integrate with respect to time for the second order rate law, where the rate is equal to some k times A squared, the integrated rate law is 1 over A is equal to kt plus 1 over A initial. And if we plot 1 over concentration of A versus time, we get a straight line with a slope equal to k. You can see here how this fits the equation of the line y equals mx plus b. And our y-intercept is 1 over the initial concentration. We can use this to determine the rate constant. We can also derive an equation for half-life where the half-life is equal to 1 over k times the initial concentration. If we plot an example of the second order rate law, we see that 1 over the concentration of A is equal to k times time plus 1 over A initial, where this fits the equation for a line such that 1 over the concentration of A would be our y, k would be our slope, and we're plotting 1 over A versus time, and 1 over the initial concentration would be our y-intercept. In this case, we get a straight line for if our equation is second order. For a zero order reaction, if we integrate our rate equation with respect to time, we get A is equal to negative k times t plus A initial. So a plot in this case of A versus time gives us a straight line with a slope of negative k and a y-intercept equal to A initial. Our half-life in this case becomes A initial over 2k. The half-life for a reaction, which is notated as t to the 1/2, is the time required for the concentration of the reactant to fall to half of its initial value. The half-life of the reaction is going to depend on the order of the reaction, because we can derive a different half-life equation depending on the reaction order. Here we see a summary of the rate laws. We see that for a zero order reaction, the rate is equal to k times A to the 0 power. And if we integrate with respect to time, we get A at times t equals negative kt plus A 0. So the slope would be equal to negative k, and our half-life expression then would be the half-life is equal to 1 over k times A0 over 2. So this is the half-life equation for a zero-order reaction. For a first-order reaction, we see that the half-life is equal to 0.693 over K. So we could also express that as 1 over K times 0.693. For a second-order rate equation, we see that the half-life is equal to 1 over K times 1 over A0. So notice that for the zero-order reaction and the second-order reaction, our half-life is dependent upon the initial concentration, but for a first-order reaction, the half-life is independent of the initial concentration. So we won't see a decrease in the half-life rate as the concentration decreases. We see here a plot of half-life for a first-order reaction. And again, the equation for half-life for a first-order reaction is T sub 1/2 is equal to 1 over K times 0.693. So it isn't dependent upon the initial concentration. So we see here that at time 0, okay, we have our full amount, our initial amount of our substance, and then after one half-life, we have half of that substance left. Two half-lives, we have half of what we had at the first half-life. After three half-lives, we have half of what we had at the second half-life. So the half-life is dependent upon the K and not the initial concentration. Here we see Conceptual Connection 15.5. The images shown here depict the first order reaction where A is going to be at various times during the reaction process. The black circles represent reactant A and the red circles represent product B. What is the half-life of the reaction? So we see here that at T equals to 0, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 black spheres. At which of these instances do we have 5 black spheres and 5 red spheres? So that would be at 90 seconds we have half of our initial substance left. Again, we'll summarize our rate laws. For a zero-order reaction, we have a rate law where the rate is equal to some K times A to the 0 power. Our units are molar times seconds to the minus 1. And the integrated rate law would be A at T is equal to negative KT plus A0, where the slope is equal to negative K and our y-intercept is A sub 0, or our initial concentration. The half-life for a zero-order reaction is T sub 1/2 is equal to 1 over K times A0 over 2. For our first order reaction, we have rate is equal to K times A to the first power. Our units are inverse seconds. Our rate law, our integrated rate law, is ln of A at time T is equal to negative KT plus ln of A0, where the slope is equal to negative K and the y-intercept is equal to ln of A0. Our half-life for a first-order reaction is equal to 0.693 over K. For a second-order reaction, we have rate is equal to K times A squared. Our units are molar to the minus 1, seconds to the minus 1, and the integrated rate law is 1 over A at time T is equal to KT plus 1 over A0. Our slope is equal to K, and our y-intercept is 1 over A0. Our half-life for a second-order reaction is equal to 1 over K times 1 over A0. If the information that we have for our reaction is concentration versus time, we can use the integrated rate laws to determine which order our reaction is observed to obey. So if we plot concentration versus time and we get a linear graph with slope equal negative K, then our reaction is going to be zero order. If we plot the ln of the concentration versus time and we get a slope of negative k, we see that our reaction fits a first order reaction rate law. If we plot 1 over the concentration of A versus time and we get a slope equal to K, then we see that our rate law is second order with respect to that reactant. Here we summarize these basic kinetic relationships. The reaction order and rate law must be determined experimentally. The rate law relates the rate of the reaction to the concentration of the reactants. The integrated rate law relates the concentration of the reactants to time. The half-life is the time it takes for the concentration to fall to 1/2 of its initial value. The half-life of a first-order reaction is independent of the initial concentration, but for the zero and second-order reactions, we have a concentration dependence.